Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 5. In this lecture, we'll discuss the pendulum. This topic is covered in Chapter 15 of our textbook by Surway and Jowett. In today's lecture, we want to discuss the pendulum. However, before doing so, we should review our main example of simple harmonic motion, which is the simple mass spring system. According to Newton's second law of motion, net force is equal to mass times acceleration. According to Hooke's law, the spring force in the x direction is equal to minus kx. By combining these two equations together, we find this differential equation here, which we refer to as the mass spring differential equation. This differential equation essentially describes the position of the mass, x, as a function of time. Based on our knowledge of calculus and derivatives of various functions, we surmise that the solution to this differential equation must be a trigonometric function. We can verify that guess by actually substituting this cosine function into the differential equation and seeing that it does indeed satisfy the differential equation. In order for this function, a cosine omega t plus phi, to be a solution, omega must be equal to plus or minus the square root of k over m. By convention, we choose the positive square root. The parameters a and phi could be any real numbers, and the function would still satisfy the differential equation. However, in practice, those two parameters are determined by the initial conditions of the mass spring system. The mass's initial position and initial velocity can be used to determine the amplitude and the phase constant. The same procedure that is used to analyze the motion of the mass spring system can also be used to analyze the motion of a pendulum. However, a pendulum has a few additional subtleties that we need to discuss. To begin with, two forces act on the pendulum bob. One force is the force of gravity or weight. Weight points downward and has a constant magnitude. We can express weight by saying that the weight vector is equal to minus mg j hat. Mg is the magnitude of the force. J hat is a unit vector that points in the positive y direction, in the vertical direction, and the minus sign tells us that the force points downwards. The second force is tension. Recall that tension always points along the string or the rope that supports the mass. In this case, tension points along the string or the radius of the circle along which the bob is moving. And although it is not obvious, the magnitude of this force is not constant. It changes as the pendulum swings back and forth. We can express this force by saying that the tension vector is equal to minus t r hat. T is the magnitude of the force. R hat is a unit vector that points along the radius of the circle, so basically along the string, and the minus sign tells us that this vector points inwards into the center of the circle, towards the center, as opposed to away from the center. We can represent these forces pictorially as follows. We can say that weight points downwards and it has a constant magnitude. So these red arrows represent the force of gravity or weight acting on the bob at various positions, and they all have equal magnitudes. Tension is a little more complicated. Tension always points towards the center of the circle along the string, and its magnitude changes. Although it is not obvious, the magnitude of tension is greatest when the pendulum is at its lowest point, and tension is the least when the pendulum is at its highest points. The sum of these two forces determines the behavior of the pendulum. A little more precisely, the sum of these two forces at each point gives us the net force, and of course the net force gives us the acceleration using Newton's second law of motion. And then once we have the acceleration, in principle we can figure out the velocity and the position of the pendulum. It turns out the acceleration vector in this case is a little more complicated than what you might expect. As you can see, the acceleration vector points in different directions at different positions, and hopefully you remember from your mechanics course that when it comes to circular motion, it is better to use a radial tangential coordinate system as opposed to an XY coordinate system or a Cartesian coordinate system. And that's exactly what we'll do. It turns out that analysis of circular motion is always easier if we start talking about components of vectors along the radius and along the tangent to the circle. As you can see, the acceleration vector is sometimes radial, as in pointing along the radius of the circle. Sometimes it is tangential, like here, where it's pointing in the tangential direction along the tangent to the circle. And then at intermediate points, it has a radial component and a tangential component. From your mechanics course, you should remember that the radial component of acceleration for circular motion is plus or minus r omega squared, where omega is the angular velocity, and the tangential component of acceleration is equal to plus or minus r alpha, where alpha is the angular acceleration. You might be wondering, why is it plus or minus? The plus or the minus depends a little bit on the conventions we use for what is the positive radial direction and the negative radial direction. It also depends a little bit on whether the pendulum is to the left or to the right of its equilibrium position. So for us at the moment, it's not really that important whether the pendulum is swinging to the right or to the left. For the most part, we're interested primarily in the magnitudes of these vectors. Let's analyze the forces that are acting on the pendulum bob in a little more detail. Since the motion is circular motion, we'll be using radial tangential coordinates. What this means is that we'll have to decompose all of the vectors into radial and tangential components. Doing that for the tension force is relatively easy. As you can see, the tension vector points strictly along the radius of the circle. A little more precisely, it points towards the center of the circle, so we can say that the tension force points strictly in the negative radial direction. Remember that the convention here is that when a vector points away from the center, we call that the positive r direction or positive radial direction. And when a vector points towards the center, we call that the negative r direction. The situation for weight is a little more complicated because it has both a radial component and a tangential component. To figure out those components, we draw a right triangle where the weight vector is the hypotenuse of that triangle, and then with a little bit of trigonometry, we can calculate the radial and tangential components. Here, theta is the angular position or displacement of the pendulum. If this angle here is theta, then this angle here in the right triangle is also theta. And then with a little bit of trigonometry, you can figure out that the radial component must be mg cosine theta, and the tangential component must be minus mg sine theta. The minus sign isn't so important for us. What's really important is the absolute value here. The minus sign can actually change depending on whether you're on the right of the equilibrium or to the left of the equilibrium. Newton's second law of motion tells us that the net force is equal to mass times acceleration. In practice, when you're using Newton's second law of motion, you need to decompose the forces into components. If you're using Cartesian components, then you need to talk about the net force in the x direction and the net force in the y direction. Here, we're using a radial tangential coordinate system, so we'll talk about the net force in the radial direction and the net force in the tangential direction. In the radial direction, we have mg cosine theta plus the radial component of tension, which is minus t, and that force must equal to mass times acceleration in the radial direction. The net force in the tangential direction is simply the tangential component of weight, which is minus mg sine theta. Tension force does not have a tangential component. We can say that's 0. and that net force must equal to mass times acceleration in the tangential direction. For us, it's the second of these two equations that's important. It turns out you could use the first equation to calculate tension if you wanted to, although that's not what we're interested in doing at this point. We want to focus mostly on this tangential equation. On the previous slide, I told you that the tangential acceleration is equal to radius times the angular acceleration. The radius of the circle is simply equal to the length of the string, so I'm going to replace radius by L, where L is the length of the string or the rod that supports the pendulum bob. You also need to remember that angular acceleration is the first derivative of angular velocity or the second derivative of angular position. If I call this equation equation 2 and I call this one equation 1, then I can substitute equation 2 into equation 1. In other words, I can take this expression for AT and plug it in here to obtain this equation down here. Minus mg sine theta, which is the tangential force, is equal to basically m times the tangential acceleration, which I've written as the second derivative of angular position. Rearranging this equation a little bit and crossing out the m's that appear on both sides of the equation, I finally obtain the pendulum differential equation. This differential equation is a second order differential equation, and it basically tells me how the angular position of the pendulum changes as a function of time. Our goal will be to solve this differential equation to find a solution for it that tells us precisely what theta is as a function of time. The derivation of this equation isn't so important, so if some of the details of what appears on this slide, if some of the details are a little bit vague or unclear, that's not so important, but the remaining discussion of the solution of this differential equation is going to be very important for us. It turns out solving the pendulum differential equation is quite difficult. A little more precisely, I should say that the solution to the pendulum differential equation cannot be expressed in terms of any of the functions that you have learned about in your math classes. The solution cannot be expressed as a trigonometric function. The solution is not a polynomial. The solution is not an exponential, and the solution is not a logarithmic function. So finding the solution to the pendulum differential equation is quite complicated unless the motion of the pendulum is limited to small angles. For small angular displacements, pendulum motion can be described as simple harmonic motion. To really understand this fact, you need to understand the small angle approximation. The small angle approximation says that sine of theta is approximately equal to theta for small angles. You can verify this fact by considering the limits of these functions. For example, the limit of sine of theta as theta becomes very small is 0, and the limit of theta is also 0. So we can approximate theta and sine of theta as essentially the same number in the limit where theta approaches 0. Another way of verifying this, and probably a more rigorous way of stating the same thing, is to use a Taylor expansion. We can use the function sine theta, we can perform a Taylor expansion about theta equals 0, and this is the power series that we would get. If you look at this power series, you can see that all of these higher order terms very quickly approach 0 for small angles. For example, if theta is already a small angle, like 0.1 radians, then theta 3 is going to be a pretty small number, and theta 5 is going to be an even smaller number, and theta 7 will be even smaller than that, and all of the higher order terms will also be progressively smaller and smaller. Which means if theta is a pretty small number, then you can essentially ignore all these higher powers of theta, and you can say that sine of theta is equal to theta to a very good approximation. Yet another way of verifying this small angle approximation is by just plugging numbers into your calculator. However, if you're going to do that, make sure you use radians, not degrees. The radian is the SI unit of angle. So for example, 1 degree is a pretty small angle. You should convert that to radians, and you'll see that it's equal to 0.0175 radians approximately. Now take out your calculator and evaluate the sine of 0.0175 radians, and you will see that it is equal to 0.0175. 2 degrees is also a pretty small angle. In radians, that's approximately 0.0349 radians, and when you take the sine of 0.0349, lo and behold, you get 0.0349. Now these are approximations, so if you included more decimal places, you would notice that there is a difference. However, for very, very small angles, you can say that to a good approximation, sine of a number is equal to that number. In other words, the result of this calculation is simply the argument of the sine function. Now, how is the small angle approximation relevant to the pendulum differential equation? Well, remember that the pendulum differential equation told us that the second derivative of theta is equal to minus GL sine theta. Henceforth, we will discuss motion that involves only small angles, and in that case, we can replace sine of theta with theta, and we obtain a new differential equation, which we will call the approximate pendulum differential equation, and it turns out this differential equation is easy to solve. We can actually solve this differential equation to find a solution that tells us the position of the pendulum as a function of time to a very good approximation. So now you might be wondering, how good is the small angle approximation? How reliable is it? How much error is there in approximating the pendulum differential equation with the approximate pendulum differential equation? A precise discussion of the errors involved in this approximation are a little bit beyond the scope of this course, but this graph should give you a rough indication of how accurate our approximations are. On the horizontal axis, we have the initial angular displacement of the pendulum. You can think of this as the maximum displacement, angular displacement of the pendulum. And on the vertical axis, we have the ratio of the exact period to the approximate period. If this number is equal to 1, then we have a very good approximation. As this number becomes bigger and bigger, our approximation is getting worse and worse. So you can think of this ratio as a measure of the error in our approximation. As this number becomes bigger, the error becomes bigger. As you can see from the graph, so long as the pendulum is swinging through, let's say, 10 degrees or 20 degrees or 30 degrees, the error in our approximation is less than 2%. However, once you have a pendulum that is swinging wildly as much as 60 degrees, then the error becomes quite noticeable. It becomes more than 7%. If you have a pendulum that is swinging all the way up to a horizontal orientation, that would be an angle of 90 degrees, then you suddenly have a very large error. That's an error of 18%. What this graph is telling you is that our approximation is quite good so long as you don't force the pendulum to swing too much from its vertical position. For example, if you're designing a grandfather clock and you want to use that pendulum to keep track of time, then obviously you want it to be pretty accurate, and you should not force the pendulum to swing too far to the left or to the right of its equilibrium. If you look at a good grandfather clock, you'll see that the pendulum really just swings maybe 5 to 10 degrees to the left or to the right of its equilibrium position. So going forward, we will continue to use the small angle approximation with the assurance that for small angular displacement, our approximation is quite good. So our goal in this lecture is to find a function that tells us the angular position of the pendulum as a function of time. In other words, our goal is to find theta as a function of time. To do that, we have to solve this second order differential equation. Solving this differential equation as written is quite difficult, so we simplify the differential equation by using the small angle approximation. We assume that the angular displacements are small, and therefore we can replace sine of theta with theta. When we do that, what we get is the approximate pendulum differential equation, which is a relatively straightforward, simple differential equation. We're now looking for a function, theta of t, so that when we take its second derivative, we basically get the function itself. Actually, we get the negative of the function itself. A little more precisely, we get the negative of some constant times the function itself. This differential equation should, of course, look very familiar to you. It's quite similar to the differential equation that we solved for the simple mass spring system. These two differential equations are not exactly the same equation, but mathematically they have the same structure. For the mass spring system, we were looking for a function x of t. Now we're looking for a function theta of t. For the mass spring system, the second derivative was equal to the negative of some constant, k over m, times the unknown function. Now the second derivative is equal to the negative of some constant, g over l, times the unknown function. So it shouldn't be too surprising that the solution to the pendulum differential equation is essentially the same solution as the mass spring differential equation. The solution happens to be some trigonometric function like the sine or the cosine. By convention, we choose the cosine function. You can verify that this function here satisfies this differential equation. If you take the cosine function and you differentiate it twice, you basically get the cosine function back with a minus sign in front of it. Of course, there are three unknown parameters: the amplitude A, the angular frequency omega, and the phase constant phi. In order for this function to satisfy this differential equation, omega must be equal to plus or minus the square root of g over L. By convention, we choose the positive square root. This shouldn't be too surprising either. If you recall, when we were discussing the mass spring system, we decided that omega must equal to the square root of k over m. K over m was the constant that was in front of x. Once again, we essentially have the same pattern. We now have the square root of g over L, where g over L is the constant that's in front of the unknown function. Of course, there are two more parameters, a and phi, and just as before, a and phi depend on the initial conditions of the problem. In other words, if we know the initial position, angular position of the pendulum, and the initial angular velocity of the pendulum, then we can solve for a and phi. So let's do a practice problem that uses the solution that we just found. Consider a pendulum with a length of 0.8 meters. Suppose the pendulum's initial angular displacement is 5 degrees and its initial angular velocity is 0 degrees per second. Find theta as a function of t. So what we have here is a simple pendulum. The length of the rod or the string that supports the pendulum bob is 0.8 meters. We displace the pendulum to 5 degrees, so we pull it, let's say, to the right by a small angle, 5 degrees, and then we release it from rest. So we don't give it a push or a kick, we simply move the pendulum by 5 degrees and then release it, allowing it to swing through its motion. Our goal is to find an expression for the position, angular position of the pendulum as a function of time. To find the solution, we're essentially going to follow the same 6-step procedure that we followed when we were talking about the mass spring system. To begin with, we'll figure out the angular frequency, omega. That's easy to solve. We have a formula for it. omega is going to be equal to the square root of g over L. On planet Earth, g is 9.8 and L is given to us as 0.8, so we find that the angular frequency for this simple pendulum is 3.5 radians per second. At this point, if you wanted to calculate the period of the pendulum, like how many seconds it takes for the pendulum to swing back and forth, you could do that. Remember that for any kind of oscillatory motion, t, the period, is equal to 2 pi over omega. So at this point, you can plug in 3.5 radians per second and find the period of the oscillations. We don't have to do that for this particular problem. It's not relevant to what we wanted to do. However, it's good to know that you can now calculate the period of a pendulum if needed. Now we know that the solution to the pendulum differential equation is a cosine omega t plus phi. We now know that omega is 3.5, so plug that in. To find a and phi, we need to use the initial conditions. Before doing that, let's calculate the pendulum's angular velocity, omega t. Remember that angular velocity is the derivative of angular position, so you can take the derivative of this a cosine function, and what you get is a sine, and you'll get a minus sign in front because the derivative of cosine is minus sine, and you also have to take the derivative of the argument, which gives you a 3.5 out front. Now we need to consider the initial conditions carefully. According to this equation in step 2, the angular position at time 0 is simply a cosine of phi. So I'm plugging in t equals 0 in here, and this equation simplifies to a cosine of phi. And that must equal to 0.087 radians. 0.087 radians is equal to 5 degrees. So I've taken the initial position of the pendulum, 5 degrees. I've converted it to radians, which gives me 0.087 radians approximately, and I'm going to set that equal to theta at 0. Remember, that's what theta initial means. Theta initial basically means theta at t equals 0. I also have an expression for the angular velocity, omega. If I plug in t equals 0 here, I find that omega at 0 is minus 3.5 times a times sine of phi, which is this expression here, and this will equal to 0 degrees per second, but I've converted that to radians, which I've written as 0 radians per second. So now I have two equations that I can use to solve for a and phi. One of the equations is this expression here, and the other equation is this expression down here. Solving these initial condition equations, we find that phi must equal to 0. And if phi is equal to 0, then a must equal to 0.087. In other words, what I did was I looked at these two equations, and maybe it's easier to start with this second equation here. I asked myself, what does phi need to be in order to ensure that the left side is equal to 0? If you want, you can take the arc sine of 0 or something fancy like that, but it should be pretty obvious to you, or hopefully you've memorized the fact that sine of 0 is 0. Once you know that phi is equal to 0, you can plug it into this other equation. Cosine of 0 is just 1, which then tells us a must be equal to 5 degrees, or in radians, 0.087 radians. It turns out there's another solution. You can also say phi should equal to pi. If phi is equal to pi, then a must equal to minus 0.087. So you can either have this pair of solutions or this pair of solutions. On an exam, either one is acceptable, although the convention usually is to choose the positive amplitude. You can now write down a precise expression for theta as a function of t. You could say theta of t is equal to 0.087 times cosine of 3.5t, or you can write it as minus 0.087 times cosine of 3.5t plus pi. There are other ways you could write this. You could add 2 pi radians to either one of these expressions and you would still get the correct answer. You could even write the cosine functions in terms of sine functions, so long as you add pi over 2 to the argument. However, by convention, at least at this point in the semester, we'll almost always prefer the cosine solution. So far, we've been discussing the motion of a simple pendulum. A simple pendulum is a pendulum whose mass is concentrated at a single point. So we've been imagining that all the mass of the pendulum that we're discussing is all concentrated inside the pendulum bob at a single point. However, in general, the mass of a pendulum doesn't have to be concentrated at a single point. In general, the mass could be distributed. In general, you can take any object with any kind of a mass distribution and turn it into a pendulum. You can take a chair and turn it into a pendulum if you want. Imagine picking up a chair, maybe tying a rope to it, hanging it from the ceiling, and then having it swing back and forth. That's essentially a pendulum. However, it's not a simple pendulum, it's a physical pendulum. So we can say that a simple pendulum is a special case of the physical pendulum. A physical pendulum is any extended rigid body suspended vertically from a pivot point and allowed to swing freely like a pendulum. So the object is extended, meaning that the mass is not concentrated at a single point. It is a rigid body, so it has to be basically a solid. It can't be like a liquid or a gas. Other than that, any such object can be suspended from a single point. We call that point the pivot point, and then we could allow it to swing freely like a pendulum. Such an object has two important points. One point is the pivot point. That's the point that does not move. That's the point that's suspended or attached to the ceiling, for example. And then there's also the center of mass. These 2 points are important because they allow us to quantify the precise behavior of this object. There's a lot that we could say about the behavior of a physical pendulum. However, for us in this class, the most important thing is being able to calculate the angular frequency of this pendulum. If we can figure out the angular frequency of this pendulum, then we can also calculate its period and its frequency, and those are often the most important characteristics of a pendulum. To figure out the angular frequency of such an object, we need to review some facts from our mechanics course. If you have such an object, gravity acts on the center of mass, pulling it down. The magnitude of gravity is going to be mg. This force will exert a torque on the physical pendulum. It is the torque that's responsible for the motion of the pendulum, for the rotational motion of the pendulum relative to the pivot point. We can calculate the torque due to weight. That turns out to be minus dmg sine theta. Theta is the angle that this vector here, d, forms relative to the vertical axis. The vector d points from the pivot point to the center of mass, and the length of that vector is important because it determines the torque. There's Newton's second law of motion, and then there's the angular version of the second law, which basically says torque is equal to the moment of inertia times alpha. We remember that alpha is angular acceleration, and that is equal to the second derivative of theta with respect to time. If we set these two equations equal to each other, we get a differential equation known as the physical pendulum differential equation. So this is the second order differential equation that describes the behavior of a physical pendulum. This differential equation is quite difficult to solve, so we simplify it. We replace sine of theta with theta. So we assume that the pendulum is not swinging wildly through large angles. We assume that the angular displacements are small. And when we do that, we get a differential equation that should look very familiar to you. We're looking for a function theta of t, And when you take the second derivative of that function, you basically get the function itself, except that there's a minus sign in front and there's some constant in front. That constant is d, which is the distance from the pivot point to the center of mass. It involves the mass of the object, gravitational acceleration for whatever planet you happen to be on, and the moment of inertia for the object. Once you have this differential equation, you should be able to immediately recognize that the angular frequency for this thing, as it swings back and forth, is simply equal to the square root of the constant that appears in front of the unknown function. So the angular frequency ends up being the square root of dmg over I. And remember, once you know the angular frequency, you can also figure out the period, because the period is simply 2 pi over the angular frequency. For us in this class, the derivation of this result is not so important. If you don't remember too much about torque and moment of inertia, that's not so important. However, being able to use this formula to perform calculations is important. And that is the end of this lecture. Thank you for your attention.